Exam 5, problem number 19. Suppose one observation was taken at random from x, which yielded the value 2. The density for x is g of x given theta is 1 over theta, x between 0 and theta, 0 otherwise. And the prior distribution for the parameter theta is h of theta, which is 3 over theta to the fourth, where theta is greater than 1 and 0 otherwise. If the loss function is x minus theta squared, then what is the Bayes estimate for theta? Sample exam problem number 19, we're asked to find the Bayes estimate under squared loss, and I'm just going to point out that is the expected value under the posterior distribution. And in exam 4, previous, I derived that to show that the Bayes estimate under squared loss is the expected value of the posterior distribution. So here we're just going to derive the posterior distribution and then find the mean of it. And so in Bayes' world, the parameter is a variable, and then after we observe the x, they're fixed. So using Bayes' formula, you can rewrite it to this, and then x is really this joint with theta integrated out. But we're given this numerator is the same as this, and we're given these two densities. So we take this and then integrate out theta. So let's do that. So f of x is we integrate, theta goes from x to infinity, and here are the two densities. We take the antiderivative, plug in our values, we get this. So then if we take this, this, and divide it by the joint density, we get this. So now to take the expected value of this, remember that the theta is the random variable in Bayes' world. So the expected value is we take this density and then put in a theta and then integrate it out to find the average theta. X to infinity, of course that reduces to theta to the fourth. Then when you take the antiderivative, you get this. Plug in the values, you get 4x over 3. And the problem asks us, hey, what if the x that we observe is 2, what is the Bayes estimate? Well, you plug in 2 here and you get 8/3. Number 20, the number of potholes on a certain highway has a Poisson distribution with an average of 3 potholes per mile. What is the probability that a given 2-mile portion of this highway has no more than 3 potholes? So number 20, we're given that the number of potholes per mile is 3, and it's a Poisson distribution. And then it talks about on a 2-mile strip how many potholes. So if x1 is the first mile, so it's a Poisson with 3. The second mile is also a Poisson with lambda 3. And so when you add those together, that's a Poisson with 6. You add the lambda parameters. And so a Poisson 6 is this distribution. And notice we put 6 in for lambda, So the probability that we're 3 or less is probably a 0, 1, 2, or 3. And then you plug in y equals 0 in here and you get this, and 1 and 2 and 3. I factor out an e to the 6th to match the answers, and then that leaves this. You add those, you get 61 e to the 6th. Problem number 21. A null hypothesis states that a random sample arises from a distribution with density function e to the minus x, where x is positive and 0 otherwise. The alternative hypothesis, H1, states that the underlying density is x times e to the minus x, for x positive, 0 otherwise. Based on the observed sample values, x1 through xn, what is the form of the critical region of the most powerful test of H0 versus H1? So number 21, They ask us what's the form of the most powerful test. And the null, and it's this. So if you put the null density over the alternative density, and if it's small enough, then we reject. So the null density is this. It's actually, they give it for 1x, which is e to the minus x. But when you collect a sample, then it's the product of those, so it ends up having a sum in the numerator. And then the alternative density is this. And then those cancel, leaving only just 1 over the product of the xi's. Well, if we take this and multiply it up, and then take the c and multiply it down, we get this for some constant c. Or you could say 1 over c, but we'll just call it c prime. Then this is the answer, but it doesn't match any of the answers given, so we have to trick it to be one of the values. So if we take the log of both sides, and then the log of a product is the sum of the logs, so that is this, and then that matches one of the answers. Problem number 22. The correlation coefficient between two variables x and y is known to be 0.8. If z is y squared, then what is the correlation coefficient between x and z? So number 22 is, it's a little bit of a funny story. Is usually I read the question and then I try to solve it, and then when I come up with an answer, I look at the answers and and it matches one of them. But here it told us that the correlation between x and y is 0.8, and then it asked for what's the correlation between x and y squared. And I just read the problem, started working, and I couldn't find it. And I have, went through several pages of scratch paper. I'm like, oh my gosh, and then usually if you're working that hard, you miss something. And so you start over and you think, man, there must be like a little trick, and I couldn't find it. And I'm like, well, what possible answers are there? Well, E says that, there is no answer, can't be obtained. So I'm like, that's it. So if you know an answer, make a comment, but I'm pretty sure there isn't one. Number 23, let x1 through xn be a random sample from a normal population with mean mu and variance 25. In testing the null hypothesis that mu is 100 against the alternative hypothesis that mu is greater than 100, what is the smallest sample size n required so the power of the uniformly most powerful test is at least 0.9 when mu is equal to 105, given that the significance level is alpha equal to 0.05. Problem 23. It asks, what sample size do we need for power? And first we need the null hypothesis that the mean is 100 against, and then the alternative is that we're greater than 100, and we want to find the power at mu equal to 105. First we need to find the rejection region. So this is the setting. It's the null hypothesis that we're 100 and the variance is 25, and for some c, we reject, and this area is 0.05, it says. So then to find c, there's a one-to-one relationship or bijection into the standard normal distribution, and so this is 1.64 that makes that 0.05. So c, and then to transform it down, you have to subtract the mean divided by the standard error associated with it, and we set it equal to 1.645. We solve for c, and now this is for a given sample size, so we don't quite know that yet. Then it says we want to make the power to be at least 0.9. So power is under the alternative hypothesis, and it's the probability that we reject when we should. And then this is also a normal, and we're calculating the power at mu equal to 105. So to transform this to a z, we subtract the mean divided by the standard error, or the standard deviation associated with that statistic, which is the standard error, and that's 0.9. Well, in the z world, that means this piece right here is equal to negative 1.28, which is this. This piece is this. So now we need to start solving for c and n. We multiply this up, and that's what this is. And then for c, we plug this in here. Then we have the minus 5. And then what we did, we just put that as an equation of n. So then I bring this piece over, and then the negative 5, I take the other side and get this. In fact, then you can show that a 5 can be divide out 5 everywhere, and that goes away. Multiply the n up, and then square both sides, and we get 8.5. But if we round down to 8, then the power is not quite 0.9, so we have to round up to 9, which that's why the problem stated at least 0.9% power. Number 24, a card is drawn at random from an ordinary deck of 52 cards and replaced. This is done a total of 5 independent times. What is the conditional probability of drawing the ace of spades exactly 4 times, given that this ace is drawn at least 4 times? So number 24, this is kind of a fun one. We draw cards one at a time with replacement, and we want to know the probability that we draw 5 cards, and we want to probably know that we draw the ace of spades 4 times out of the 5, exactly 4, given that we've drawn the ace of spades at least 4 times. So let xi be the ith draw, and we draw an ace of spades, and that's binomial 1 with a probability parameter of 1 over 52. Someone would just call it Bernoulli, but I always call it binomial. We're interested in the 5 draws, so the sum of these, and that's we're going to let that be y, and y is binomial 5 1 over 52. So ultimately we're interested in this probability, but we have to calculate this one first. So we're going to do that. The probability that y is greater than 4 is, probability that we're 4, and probability we're 5, which is this probability we're 4, y is 4, y is 5, simplifies to this. And I don't expand this because using conditional probabilities, that reduces with something in the numerator. So this probability, what we're interested in, is this. And the probability that y is equal to 4 is just a binomial. And then we calculated this, and then that numerator cancels with this, and it leaves 255 over 266 as the answer. Number 25. Which of the following is true of a 95% confidence interval for the mean of a population? So number 25, it asks about a confidence interval, and specifically a 95% confidence interval. And just briefly, a confidence interval is not a probability statement. A confidence interval is a frequentist viewpoint, which means if you do it long enough, do the same thing long enough, you're going to be correct 95% of the time. And so what that means is if you take a sample size n, calculate the confidence interval, and it may or may not include the true parameter of interest, mu, but then you take another sample of size 100, calculate the confidence interval. It may or may not calculate or encompass the true population mean, but if you do this long enough, to infinity, those 95% of those confidence intervals that you calculated capture the true mean. So it doesn't say anything about the confidence interval covering half, a certain percent of the population. Matter of fact, as the sample size gets bigger and bigger, the confidence interval goes smaller. So it's not a statement about that. It's not a statement about how many of the sample values it covers. It's not a probability. Some people interpret it as that the probability that this captures the mean is 95%, and that's actually false. It's either 1 or 0. 1 if the mean is in it, and 0 otherwise. So confidence intervals it's a frequentist viewpoint. You do it long enough and you're correct, 1 minus alpha percent of the time, or 95% of the time. So the answer is E. Number 26, suppose that x is a random variable with density function f of x equal to 3x squared over 8, x between 0 and 2 and 0 otherwise. Let y equals m times x squared, where m is a fixed positive number. What is the density function of y, and where is it non-zero? So 26, we're asked to find the density of y, which is mx squared. And then x ranges from 0 to 2, which plays an important part because in general, x squared, for all real numbers is not a one-to-one function. And so this transformation can be tricky. And then you have to break it up into disjoint sets that, mutually exclusive but encompass the whole range. And then you have to find this transformation over each of those disjoint sets. But since it's positive 0 to 2, x squared is a one-to-one function. So we can proceed pretty nicely. So we back solve for y. And notice that this isn't plus or minus because we're only dealing with positive values of x. So it's the square root of y over m. Take the derivative, we get this. So then the density of f of y it's f of x, but you plug in this value of x, and then you take it times the absolute value of this Jacobian. So it's 3/8 x squared, but we use this in place of x, and then this is the Jacobian, or this piece. And then this simplifies to this, where y is between 0 and 4m, and that's the answer. Hope you enjoyed it. There's more to come. We're going to go through all 8 tests. Subscribe if you're interested in being notified when they come out. Talk to you later.